I think she probably feels welcome now. So. All right. Ladies and gentlemen, class recording has started. So, yesterday we started talking about phase changes or changes in states of matter. First, are phase changes physical changes or chemical changes? They are physical changes. Why do we know they're physical changes? Say again? The composition doesn't change. It's still the same substance. It just has a different appearance, right? Some properties changes, but some properties change, but the composition has not. Okay, we talked about that there are two factors that determine what state of matter something exists in. What are the two factors, according to kinetic theory, that determine what state of matter something exists in? Attraction between the particles and temperature, and the temperature tells us what about those particles? Yes, how much they move. That's right. But yeah, that's what you said. How much energy they have is also true as well. Okay. All right. Meaning, if we are going to change the state of matter that something exists in, we either have to change the motion of the particles, or the attractions between them, or both, in order to get it to move from one state to another. Okay? The easiest way for us to do that is by changing the energy, or changing the motion. And we do that by changing the temperature. All right? So, we talked yesterday about the difference between an endothermic change and an exothermic change. What's the difference between endothermic versus exothermic? Alyssa, go ahead. The exothermic process releases heat, like absorbs heat, right? So here are, here are the 6 phase changes, right? Which of these phase changes is endothermic? Give me one of the endothermic phase changes. Zach, what's one of them? Melting. Why is that endothermic? What do we have to do to the energy of those particles? They have to move a little bit faster, right? Going from the solid phase to the liquid phase, we have to move those particles faster. So melting is an endothermic process. What else qualifies as an endothermic process? So what's another one? Vaporization, turning a substance from what to what? Liquid to a gas. And then finally, the last endothermic process that's up there is sublimation, which is turning it straight from a what to a what? Solid to a gas. Okay? Now the reverse process, right? If we release energy to the surrounding, it's because the particles themselves have lost energy. The motion has decreased. Those particles have decreased their energy, but because energy is conserved, right, it just can't go away. So we just release it as heat, right? So, what are our exothermic changes? Do you have a question or do you want to? Okay, go ahead. Okay, sublimation. Have you ever seen dry ice before? Okay, dry ice is a substance that sublimates. When if you put a piece of dry ice on the table, it doesn't melt. It doesn't turn into a puddle, right? It just vaporizes away. So that's a substance that goes straight from the solid phase into the gas phase. Okay? That's like the most famous example of sublimation. All right, Hannah, do you want to answer the endothermic question or the exothermic question, or do you want to?
No, I haven't done that one.
Okay, go ahead.
What's an example of deposition?
Okay, did we not talk about deposition?
We talked about what it was.
Okay, so frost on the window in the wintertime, right, where that water vapor that's in the air goes straight into the solid phase without passing through like the liquid phase.
Okay, then your question.
Oh, so exothermic changes. What are the exothermic changes that are up there on the board?
Freezing.
Freezing is an exothermic change, right? Condensation, turning something from a liquid to, or from gas to a liquid, right? Deposition, so turning something straight from the gas phase into the solid phase. All right, good? Okay. let's talk about how these factors that affect the state of matter that something exists in are measured. All right, here's a graph that you have that's on the back of your outline. We'll start getting in the habit of doing this as we examine graphs more, but the first thing we need to do is we need to identify what this graph is showing us the relationship between. What labels do we have on our axes here? So, what is this graph showing us a relationship between? Great, go ahead. Oh, go ahead. Temperature and heat, right? So temperature and energy. And for the most part, what do we see about the relationship between the energy that we add, or the heat that we add, and the temperature? Go ahead. As the temperature gets higher, the energy gets higher, or vice versa. Okay? But what are we seeing about certain portions of this graph? Jay, go ahead. It's flat. It's flat along which or the fact that it's flat is telling you what about those portions of the graph? What's constant? The temperature is constant. So there are certain portions of this graph where the temperature remains constant, right? This section of the graph right through here, and then this section of the graph right through here. What's not constant, though, during those portions of the graph? The heat, the amount of energy that we are adding. So we have portions of this graph where we are adding energy to this substance, but the temperature is not changing. Is that good with what that graph is telling us? Okay. All right. Now, the title of this graph says it's the heating curve for water. Hopefully, because you know a little bit of background information, the first constant temperature that we run into is which temperature? 0, but it's 0 what? Celsius. What happens at 0 degrees Celsius? Water freezes. What else can water do at 0 degrees Celsius? It can also melt at 0 degrees Celsius, depending on whether we are putting energy into it or whether we are taking energy out of it. Right? In this case here, would this represent water melting or freezing at 0 degrees Celsius? Starting off colder than 0, holding at 0 for a while, ending up warmer than 0. This section right here is water melting. Exactly, right? And so, Elizabeth, you'll see this actually in your lab you'll see this in your lab on Monday. Not to like spoil it or anything like that, but we are going to start with something that is a liquid and watch it turn into a solid. So we'll see this coming from a different angle, right? All right. The second constant temperature that shows up on this graph is where? 100 degrees what? Celsius. What happens at 100 degrees Celsius?
Water boils.
Water boils, right? It turns from that liquid phase into a gas phase. So, what is this graph telling us about the temperature of a substance during a phase change? What does this graph tell us about the temperature of a substance during a phase change? It is constant. While that substance is going from one state of matter to another state of matter, there is no change in the temperature. If we look down here in the bottom left-hand corner, this would be water existing in what state of matter? Frozen. Ice cubes, right? In this section right here, right, that would be water existing as what state of matter? Water, liquid water. But during this section of the graph, what would we see in our container? A mixture of solid water and liquid water. And it will remain the same temperature until all of it transfers into the liquid phase. Then it will start increasing in temperature again. Okay? So, as far as your outline goes, as we saw from this graph, and as you'll see in the lab on Monday, when the temperature, or when a substance is changing states of matter, or going through a phase change, the temperature of the substance does not change. So, this presents us with a little bit of a problem. Because what is still happening during that phase change, at least according to that graph we were just looking at? The heat is still being added to it, but the temperature isn't changing. So where is it going? Well, we said that there are two factors that determine the state of matter that something exists in. What are the two factors that determine the state of matter that something exists in? Attractions and motion. If the temperature isn't changing, what's not changing? The motion isn't changing. So where does that energy have to be going towards? The attractions. Okay? In order for something to become a liquid, two things have to happen. One, the particles have to move more, and two, what else do the particles have to do? Spread apart a little bit. Not a whole lot, but a little bit. So during that time in the graph, during these flat sections of the graph, that's when those particles are moving a little bit farther apart in order for them to move into that next phase. The energy that is being added during that phase change is going to either ordering or disordering the particles, depending on whether they're going from a solid to a liquid or a liquid to a solid or whatever, but the actual temperature doesn't change. Let's go ahead. Yeah. So the making or breaking of attraction should go in that spot there. And attractions is kind of in quotation marks because that's a simplification of what we're describing there, but for the level you guys are at, that's what we're going with. Okay? Unless you know about like polarity and electronegativity.
We learned about that.
Okay. We learned about it before.
It makes the Zolus as well.
Oh, okay. Well, substances that have more polarity are harder to break apart. Water is actually a pretty hard molecule to melt because there's a lot of polarity in water, so they hold on to each other a little bit more. That's why, like this, right? Okay. What is the active ingredient in this? Alcohol. All right. How hard is it to get alcohol to evaporate?
Not
Pretty easy to get it to evaporate, right? All you gotta do is rub it on your hands for like 2 seconds and it's gone, right? But if you filled your hand up with that much water, if you rubbed your hands that long, would the water be gone? No. It's harder to turn that water into the gas state because it has more polarity and more attractive. I didn't
It
even know.
smells so strong.
It's all good. It is hard to freeze alcohol, yes. So it freezes at a lower temperature than water does. And again, it has to do with the fact that to get something going in solid state, there needs to be more attraction, right? So if something attracts each other more in the liquid state, like water does, than alcohol does, it's also going to be easier for it to go into the solid phase because those attractions are stronger. Is that good? All right. Good with this idea. We good with that? Okay. So finally, the last thing we want you to look at here. Okay. Oh, sorry. Analogy. Forgot the example that came up with the thing just then. All right, so we talked about the other day that you guys during your school day represent like certain states of matter, right? Right now, what state of matter are you guys representing? Solid, right? You're sort of in one spot, but does that mean you're not moving? No. You're still got a little, you're writing or you're, nodding your head off, you're falling asleep, or whatever it is, okay? But there's still a little bit of motion there. Transitioning from the solid phase to the liquid phase happens when? In terms of your school day? End of the period, when the bell rings, right? Okay, now, do you immediately go from sitting in class to walking in the hallway? No. Right? You don't just get up and go, right? There's stuff you have to take care of beforehand, right? First you stand up, then you got to put all your stuff away, then you got to pack your backpack up, then you got to put your backpack on, right? That whole scenario takes place as you are standing right there by your seat. That transition has to happen before you can go from solid to liquid. That's what's going on here. Those attractions that are holding those molecules together in the solid phase have to spread apart a little bit. And once they spread apart, now all those molecules can start moving a little bit faster. But there has to be that transition phase before it can happen. Okay? Good? All right. Phase diagram. Two factors that determine the state of matter something exists in, right? What are the two factors? Attractions and motion. Okay? So, a phase diagram is a graph of temperature versus pressure. A graph of temperature versus pressure. What does the temperature describe for us in terms of the particles? Motion, right? The temperature takes care of the motion part. So that means what does the pressure kind of represent? The attractions part. Okay? So this graph, temperature affects the motion of the particles. So that's one factor that they're trying to, that the graph is trying to show us. I think so, yeah. Yeah, temperature affects the motion, right? But then pressure determines how close those particles are together, which affects the attractions. Okay, good? Good then? Got it? All right, so let's go here and let's take a look at this phase diagram that you have down in the bottom left-hand corner. Okay? Don't worry about that big red triangle over on the side. That's for something that I'm going to do here in a second. Okay? All right. Here's our phase diagram for water. Phase diagrams are graphs of temperature versus pressure. Notice temperature on the x-axis, pressure's on the y-axis. Okay? You'll see there are these three red lines that split up this graph into three separate portions, right? Here's this, sorry, purple lines, I guess. Here's this purple line right here, right? Here's this purple line right here. Here's this purple line right here, okay? Come on. So purple line here, purple line here, purple line here. It splits up the graph into three big sections. Notice that the section on the far left is labeled as the solid phase, right? The section right in the middle is labeled as liquid, and the section on the right is labeled as vapor, which is gas. Okay? All right, let's look at the x-axis. The solid phase is on the far left portion of this graph. What's true about the temperature in the far left portion of the graph? Well, let's say for general purposes, it's lower, right? The lower the temperature is, which state of matter are we more likely to find our substance in? In solid phase, right? These are frozen things. Well, whether that's, frozen really, really cold or just frozen below the freezing point, that depends on the substance we're talking about. On the x-axis over here, as we move to the right on the x-axis, what's happening to the temperature? It's increasing. What state of matter do we find over on the right-hand side of the graph? The vapor phase. As the temperature gets bigger, right, the vapor, we're more likely to find something in the gaseous phase. Go to the zone. Yes. So let's look at a couple of important points on this graph. So I drew this red line and this big triangle over here is just so I can move the red line a little bit easier, because it's something easier for me to click on. Okay. So, oh, these are supposed to be connected. That is, wow. Sorry, everybody. Okay. Hopefully they'll stay connected. So. What? I hope they don't. All right. So on the y-axis, we have the pressure labeled. And you'll see that the label on pressure says ATM, atmospheres, is what that stands for. That pressure at this line right here, 1.0 atmospheres, represents like the normal pressure that exists here in this room in Westlake, Ohio. Okay? If you notice, this dotted line, the horizontal dotted line, and this vertical dotted line that starts down here intersect right on the purple line. What do we call the boundary between the solid phase and the liquid phase? What happens at the boundary between solid and liquid? Melting happens at the boundary between solid and liquid, right? If we're going this way, if we're going to the right on the temperature scale. What happens if we go to the left on the temperature scale? Freezing, right? So these two lines intersecting give you what's referred to as the normal freezing point. Here in Westlake, water freezes at 0 degrees Celsius. Over here on the right, what do we call the boundary between the liquid phase and the gas phase? Vaporization, turning something from a liquid to a gas. At 1 atmosphere, we hit that line at 100 degrees Celsius. That's the temperature that water boils here in Westlake. Okay? Good with that. All right. Watch this. Ready? Okay. I just moved our classroom from Westlake, Ohio to Denver, Colorado. All right. As we go to higher and higher elevations, the pressure is decreased. Like your outline says, what happens if we decrease the pressure to the attractions between those particles? What happens to the amount of attraction that those particles? There are less attractions between the particles at a lower pressure. Look what happens to, look what happens to the temperature where the red line intersects the boundary between liquid and gas. What temperature does water boil at higher elevations? Is it 100 degrees Celsius? Nope, a little bit less. If you read your box of mac and cheese, okay, or if you read instructions for like baking cupcakes or something like that, they have directions, but then a lot of them will have high altitude directions. Look at your box. So, why do we need high altitude directions to cook your mac and cheese? It boils at a different temperature. What temperature does the water boil at in Denver? 95 or something like that, right? That means, though, that that water is on your stove and it's boiling. It looks like it's boiling just here in Westlake, but it's not as hot. So what do you have to do with your food? You have to cook it longer because it's not as hot. Okay? All right. Next, I'm going to do this. Let's see if they stay connected. I'm pretty sure they won't, but that's good. Okay. All right. I took my red line down really, really, really far.
Where are we going? Where are we?
Okay, hold on. Hold on. I gotta get this. I gotta get my pink line. Gotta get my pink line here. Ah! Come on, pink line. Oh, crud. Here, let me do this. All right. Let's go here. Okay. So, I've taken the pressure down really, really, really far. So the amount of attractions between my particles is much smaller now. How easy is it for them to separate into the gas phase now? Very easy. Real easy. We don't have to make them go very fast to get them to turn into a gas. That line right there is the pressure at approximately 63,000 feet above sea level. I know that Everest is only about 29,000, okay, so about 3 times as high. But it's important because that temperature, even though I didn't draw my line straight, but pretend like it is, okay? That temperature at that height, the temperature at that height where water turns into a gas phase is about 37 degrees Celsius. That may seem like a random number, but does anybody know why 37 degrees Celsius is important? Your body temperature is 37 degrees Celsius. Meaning, at that body temperature, at that altitude, water boils at your body temperature. That's not good for you. Essentially, hold on a second, just a second. Essentially, that altitude is what we would consider space. Because you can't be there unless you have a spacesuit on. Okay?
Oh, because your blood would boil.
Exactly.